Electrical wiring. I'm going to make a short mention of AC electrical wiring first. That's the electrical wire type you might use when plugging into the domestic or commercial grid. Just so we have a rough idea of the basics of wire types. And then I'll go into DC wiring a little more extensively. You might note that the power leads that run to domestic appliances, such as lamps, bedside clocks, toasters and the likes, are fairly flexible and not particularly thick and heavy. However, if you have an electric cooker and you can see the wiring that runs to it, you'll note that the wire is pretty thick and stiff. And the same with air conditioning units. They tend to use a thicker wire than what your toaster might use. The thicker wires are usually indicative of the device needing a higher power consumption, but by and large, most domestic devices use a fairly lightweight wire. The term used for the weight or thickness of a wire is gauge. Its measurement units are often relevant to where in the world you are located. For example, in the USA, they use a system called AWG, or American Wire Gauge. The thinner the wire, the higher the AWG number. The thicker the wire, the lower the AWG number. AWG1 would be the thickest, and AWG40 would be the thinnest. However, in most of the rest of the world, the metric squared system is used. For example, 10 millimeter squared, which would be represented by the number 10, of course, then mm for millimeters, and then a little number 2. The little number 2 indicates squared, if you can remember some of the more advanced math lessons in school. However, that would be 10 mm and the little number 2 representing squared. Now, 10 millimeter squared does not actually equate to 10 millimeter in diameter. It would actually equate to 3.6 millimeters in diameter. But we're not going to get too much into the math of wire gauge specific. There are two aspects to a wire's makeup. The conductor, which is the metallic aspect of the wire, in which the electricity travels, and there is the insulation, or the covering sheath, sometimes made of plastic or some other non-conducting material, that protects the inner core of the wire from damage and also stops people touching the conductor and possibly getting an electrical shock, and again, also stopping the wires from touching one another. The conductor of the core of the wire is usually what is measured when the gauge of the wire is being stated, not the outside diameter of the insulating sheath. The sheath itself may be specified as lightweight, flexible, or heavy duty. Thin wall is probably the most likely sheathing you're likely to use. You should figure out what wire sheath is best for whatever application you're using it for. I will make some suggestions later. Another thing that is seen in AC, probably more than DC wiring, is solid core conductor wiring. Rather than thin strands of wire, there is just one rather stiff rod of wire acting as the metal conductor with a sheath around it. You don't see this too often in DC wiring. An interesting note is, electricity tends to flow around the surface, or skin, of the metal conductor wires. So if there are a lot of smaller wires making up a larger bundle, then electricity will flow better, as there is more surface area. Stranded wire is made up of lots of finer wires that make up a larger gauge of wire. This making stranded wire more efficient and often more practical because of its flexibility. Now, let's talk conductor materials. Copper is the most extensively used material in wiring as it holds up well and conducts electricity well. Gold and silver also conduct electricity well. However, they are significantly more expensive, so are almost never used. Aluminium wire is considered rather low quality. Now on to a rather important aspect of this tutorial related to DC wire gauge. In a word, resistance. I'll explain. Resistance is quite an issue in the low voltage DC world. If you're trying to push any amount of power down a wire that is too thin, then you will experience resistance. Just like a tube that is too thin for the amount of water you might want to flow out the end. Too thin an electrical wire in a DC circuit reduces the amount of current flow. I won't get into the fact that if a wire is too thin, the wire will also warm up. The heat in itself gobbling up some of the electricity, not to mention the possible fire hazard. But the voltage will also be affected and reduced, hence the wattage diminishing, or power in general diminishing. It's not just the gauge of the DC wire being too thin for an application, it's also the length of the wire can also be too long. In DC electricity, it is very important to get the gauge of the wire correct, based on the length and power demands being made on it. A longer stretch of DC wiring will need a thicker gauge wire, so as to not lose electrical power as it travels down the wire. Heavier gauge wire is always better in the DC world, but obviously heavier wire costs more. So we try to find the best gauge of wire for this specific application, taking length of run and electrical demands on the wire into consideration. For example, a friend of mine wanted to put an LED battery voltage gauge up in his camper van so that he could monitor the state of charge of his recreational leisure battery. The location he wanted to put this LED gauge was a meter or so from the battery, and he was also planning on using power from the same location of the battery monitoring LED gauge using the same bus wire. Bus just meaning a shared wire, to power a low voltage, high amperage, that is, high wattage, fridge. This being the case, so that he would get a correct reading from the LED battery gauge, a heavier electrical cable should be used. 1, due to the wattage amperage draw of the refrigerator. 2, to give a realistic power figure represented on the lead gauge, without power drop-off due to the electric wire cable struggling to give an appropriate amount of voltage wattage amps. In short, the wire had to be heavy enough, or of a thick enough gauge, to not allow the high power draw of the fridge to overly affect the LED gauge's ability to get a realistic reading of the state of charge of the battery, or its true voltage level at any given time. So in this kind of scenario, what kind of wire are you going to use exactly? So in my friend's case, he was using a lead acid 12-volt nominal system, nominal meaning kind of average, and he was definitely not going to be pushing a whole lot more than 12 amps. I'd be surprised if he pushed 6, actually, even with his refrigerator plugged in. And the cable run up to where the LED gauge and the outlet or power plug socket, which he was utilizing a cigar lighter type socket, that was not a whole lot more than 1 meter away from the battery source of power. Because he had an LED lamp, LED gauge as part of this equation, I wanted the voltage drop to be as minimal as possible, which would be 1%. You can't get away with 0%. There's always a little tiny bit of loss, but 1% would be okay. So we got 1 meter, we got the voltage, nominal voltage at 12 volts, and current amps I didn't believe would be any more than 12. It's quite high. You could build upon that. So anyway, I decided on suggesting AWG10 or American Wire Grade 10, or some in the region of 5mm squared wire, which I thought was adequate for his purposes. AWG10 5mm squared wire would be adequate for other wiring. If he wanted to extend wiring further down through his cabinetry, another couple of meters or so, and maybe have another cigar lighter socket at the other end of his van, or maybe 2 cigar lighter sockets, at which he could then plug in USB adapters, USB charging adapters, or so on and so forth. And this wire would be more than sufficient for that purpose. So in general, yeah, I think the AWG10 5mm squared wire was going to cover most of everything he might need in the rear of his van, even supporting the diesel heater he has there, the electric fan, and the glow plug factor, which I think they don't use a whole lot more than 4 or 5 amps initially, and then they drop down to about half an amp. What I've suggested to him is perfect, but it allows for it later on expansion, so you could grow from it. It's a good foundation. So I think that's pretty much the DC wiring world covered. The AC we covered earlier. I'm not really going to go heavily into AC because the idea of these tutorials is aiming towards leisure recreational vehicle type wiring usage for battery-based systems, DC battery-based systems. So the one thing you really need to keep in mind is wiring is very important, actually. It's often overlooked by a lot of people doing build-outs, not realizing the importance of the gauge of the wire in varying applications, depending on the usage demand, keeping in mind further growth. So you need to lay a good foundation of wiring and heavy-duty enough wiring to potentially carry future projects. In addendum, there is also should be taken into account is different voltages. It's not always going to be 12 volts. It could be 24 volts. It could be 48 volts. In this case, you should look up the wiring maybe on charts on Google or for wiring charts, DC charts. There are also calculators out there that can be Googled on the internet that will aid and assist in getting the correct wiring gauge for these higher voltages. And technically, as the voltage gets higher, you can use a thinner wire. So if you're using 24 volts, you're going to use a slimmer gauge, a thinner gauge if you were using 12 volts. And also 48 volts will again use even a thinner gauge wire than, let's say, 12 volts. So you might want to go out on Google and look for a DC wiring voltage calculator. Into that calculator, you'll need to enter the length of your wire, or the projected length you believe you might use. You're going to have to enter the amperage, or the maximum amperage you believe you might be using. And of course, you're going to have to enter the voltage as well. And it will calculate what it believes to be the ideal gauge of wire you might use in such a scenario.